I'm a postdoc at Hebrew U and UCC, and today I'm going to talk about shapes of galaxies. So the motivation of our work comes from the recent results from the Kendall survey. So here we have the Vanderbilt results. He looked at the projected shape of galaxies, and he was able to infer the fraction of galaxies that are intrinsically elongated or spheroidal, and his conclusions are that at high redshift, there's a higher fraction of prolate, elongated system, and low mass, but at a lower redshift, most of the galaxies are oblate. These results has been also confirmed by another group, by Takeuchi, with a different sample. So basically, the questions that we want to answer are, why do galaxies change their shape, and when do we have this transition from prolate to oblate spheroidal, and if this depends on mass and other properties. So there has been some preliminary work from simulations. So for instance, we have dark matter-only simulations that looked at the shape of dark matter halos, and for example, Allgood is one of the most studied papers in this field, and their conclusion is that dark matter halos are prolate at early times, which is consistent with observations of galaxies, and they also show that they are more elongated or lower radii. There has been some preliminary work in hydro simulation, in particular Severino 2015 looked at low mass galaxies of the Vela simulations, and he concluded that indeed you have very prolate system at high redshift, and when the galaxies grow in mass, you become more rounder both in stars and dark matter. And he also noted that when you're dark matter dominated, you're more likely to be elongated. And he said when you're baryon dominated, your galaxies tend to be oblate. So our goal is basically to extend the work of Severino to the entire sample of the Vela simulation. So let me walk you through the Vela simulation suite. It's a collection of 34 zoom-in simulation at very high resolution. There have been some talk by Avishai and Colin. They already went through some dealers of the simulation. So basically, what I want to show you here is just the mass range that we're going to be looking at. So this is the virial mass of redshift 2. So we're going from mass as small as 0.07 times 10 to the 12 for Vela 5 up to 0.9 times 10 to the 12, so almost a Milky Way sized galaxy for Vela 7. So we have a fair large range of masses to explore the shape. So now let me tell you very quickly what Avishai was talking about before, that most of these galaxies go through a compaction event, which means that at very early time you were in a diffuse phase. You can see from the gas is not very low, but then at some point a lot of gas is brought in the galaxy and you compactify and you have this blue nugget phase, and then afterwards you quench. And what I want you to focus on is not the gas line, actually, it's the dark matter and the stellar line, and you can see that in the diffuse phase your dark matter dominated. And then in the compaction phase, you can see that dark matter and stars are roughly equal. And then in the quenching phase, you're baryon dominated. And most of the galaxies have this feature. When you compactify, the transition from these two regimes happens when you become self-gravitating in the core. So I just want you to remember this for what I'm going to say you in a minute. So now let me tell you how we measure shape. There are many methods out there. And what I prefer to do is to use the so-called shape tensor, which is defined here, which is basically very similar to the inertia tensor. And the assumption that we make once we compute the shape tensor is to assume that the shape of the galaxies can be described by an ellipsoid, which is a fair approximation actually for stars and dark matter, not so much for gas, especially at high redshift, as I will show you later. But so after this assumption has been made, we can compute we can diagonalize the shape tensor and get the eigenvalues and eigenvector, so we can quantify what kind of ellipsoid we're looking at. So we assume this convention about for our eigenvalues, and we basically define three different classes of ellipsoids. We have prolate elongated systems that sort of have like a cigar shape. Then we have oblate, ellipsoid, or triaxial. And you also have spheres, but sphere is as a subclass of the triaxial systems. So that's our main classification, and in the literature you see people have been using this parameter to sort of like classify the shape in a very simple way, which is called the triaxiality. And here we have, depending on the values of this t, you can actually distinguish between the three classes. But the problem with the triaxiality is that for a sphere, t is ill-defined. It can get any value from 0 to 1. So you want to do a little bit better. And actually, what we suggest is if you want to study the shape of a system, it's better to use 2 parameters instead of 1. So what we're using is actually called the elongation, defined here, and flattening. And if we plot these, if we use these 2 parameters, we can define a shape plane. And so we have different regions depending on the intrinsic shape of a system. So here you have a prolate region, here an oblate region, here in the close to this line we have triaxial systems, and down here we have spheres. So in this way you can really study much better the evolution of the shape. So now let's see what happens if you look at one particular galaxy. This is Vela 28, and you will also see in Severino's paper. So this is why this is here, just to compare with these results. And so we look at a very early epoch, just before compaction. You can see the stars, dark matter, and gas are very prolate. And those are all just the different projections, and this is our best fit ellipsoid. For the gas, I told you there is a bit of an issue at high redshift because the gas doesn't really look like an ellipsoid at all. So that's the situation before compaction. But then after compaction, at about a redshift of 1, we see that the stars and dark matter have puffed up and they look more spherical, and they're actually classified as triaxial. And the gas, you can see, as set into a disk, but in this case, the disk is not so thin. But still, it is a disk. So we basically repeat this experiment for all of the galaxies over sample, and we have about 1,100 snapshots, and then we stuck all of the results together to see if there's a pattern, and this is what we find, as I showed you before. So this is the EF plane for dark matter, stars, and gas. As you can see, the color code is dark matter mass over baryonic mass within the innermost 1 kpc. You can see that when the dark matter dominates, we have stars and dark matter start out prolate, and then as soon as the core becomes baryon dominated, you evolve into a more spherical configuration for the dark matter, and into like a disky configuration for the stars, disky oblate. And then gas, they're ill-defined at high redshift, but then they become perfectly disky at low redshift. So now let me go quickly through this plot. I have the X-axis plot, and just want to color this by different properties. So for instance, now we color for sigma stars, measure at the effective radius, and you can see that here we have very diffuse systems, and then they compactify here. And actually, the transition from prolate to oblate system roughly happens at the typical surface density for compaction. Then another interesting property to look at is the circular velocity, and the transition between the 2 regimes happens at about 100 kilometers per second. I'm going to tell you more about this in a second. And also, we can color by specific star formation rate. So here we have very star-forming systems, and on the left of the diagram we have very quenched galaxies. So we've seen basically that the transition from prolate to oblate systems is very correlated with compaction. And the parameter that is regulating compaction, as claimed, as argued in the Zolotov paper 2015, is actually self-gravity. And so now let's put this everything in a diagram. We can see here the redshift at which the galaxy becomes self-gravitating versus the circular velocity at this redshift. So you can see that when the galaxy becomes self-gravitating, this seems to happen at the exact same velocity, which is 100 kilometers per second, and which is the critical velocity below which you have, above which the feedback, the outflow is inefficient. Yeah, that's what I really mean. Yeah, that's what I mean. Yeah. And then we also look at the direction between the different components, the alignment. And here, very briefly, I just plotting the cumulative distribution of the cosine of the major axis between stars and dark matter, gas and stars. And here you can see that in the baryon dark matter dominated phase, stars and dark matter are mutually aligned, but then the alignment is kind of random when you move to the baryonic phase when your system becomes spherical. So you don't have a very defined major axis anymore. And also, very briefly, when you're in the baryon dominated phase, you can see you're more aligned actually with the minor axis of the gas because you start to form a nice disk. Then we try to explain why we have what's behind the elongation, and we can see, so what we looked at, we measure the shape tensor at the effective radius and the shape tensor on much larger scale, about 2 radii, and what we looked at is the cosinus of the major axis of these two tensors, and we can see that we have a very strong correlation. We have a very small angle when the system are elongated. So this is telling us that elongation is driven by the fact that a dark matter core, the halo forms within a filament. And also, to make this point even stronger, we looked at the velocity dispersion, and what we did, we colored the points now by the angle between the major axis of the sigma tensor, which is the stress tensor, and the shape tensor. And you can see that basically velocity is supporting elongation for the dark matter in the elongated phase, also for the stars. But then when you move to the oblate phase, you see that you don't have a very good alignment between velocity and shape. And also, we look at the torques, the action of the torques. In particular, we measure the, let's just say the angular velocity. The torques are able to rotate an object along its minor axis, and we quantify the strength of the torque with this parameter, which is basically telling you if this parameter is 1, it's telling you the torques are able to rotate significantly a structure along its minor axis within an orbital time. And what we see here, you just look at the orange points that at very high redshift, when dark matter dominates, torques are stronger, and so they're able to effectively align the different components. And we also speculate that because torques are stronger, this can also be another compaction mechanism because they can bring more gas in. But then obviously when you go to the more oblate phase, because the system becomes spherical, the torques are weaker. And yeah, so we have these pictures consistent. Then I see 1 minute, right? I just want to talk to you very quickly about another work in progress that we have. So now I just want to look at 2 galaxies, their evolution in the shape plane. Vela 7 is our most massive galaxy, and Vela 8 is one of the low mass galaxies. You can see that Vela 7 actually becomes very oblate and low redshift, but Vela 28 does not. And the difference between these 2 galaxies is actually that Vela 7 compactifies at a density, as a stellar density of about 10 to the 9 solar masses per kiloparsec square, while this galaxy compactifies at a density which is about an order of magnitude lower. And so the idea behind what's happening here is that when you have a central compact concentration, you destroy box orbits more. So the more concentrated you are, the more you tend to become oblate. So that's all I wanted to say. I have a few slides for questions, just...
That wasn't even
Okay.
that's someone else.
Okay, maybe it's my timer, so that's perfect.
All right.
I just want to leave you with my conclusions, and yeah, I also have a few slides about projections of shape, if you want to ask me that. It was just another project that we're doing, but I'm pretty much done. So thank you for your attention.
Questions. And while we're having the questions, if Guillermo could go and set up. Brent.
Whenever I hear about the relative distribution of stars and dark matter in galaxies, at least for spheroidals, I think of the fundamental plane. Have you looked at how the fundamental plane might evolve in your simulations?
No, we did not. We did not look at that. Maybe it's something that we should be looking at. So thank you for suggesting, but no, I can't give you an answer for that because we really haven't looked.
Other questions? Frank.
When you look at shapes of dark matter halos in simulations, there's always a big transition that occurs when you go basically from below M star to above M star, the characteristic mass. So I could imagine that also in the topology of the feeding streams and everything changes. You must be bounding just about M star values at around redshift 2. So have you looked at whether you see transitions occurring at a particular mass scale? You're covering almost 2 orders of magnitude in mass?
You mean if there's a correlation with the shape and mass somehow?
Yeah, and the halo mass?
What I did is that I took different beams of mass and I tried to measure the average shape. And what I find is that regardless of redshift, if you have a low mass system, let's say between 10 to the 8 and 10 to the 9 solar masses, you tend to be significantly more prolate than high mass systems. So galaxies that are about 10 to the 10 are always oblate. They're never prolate. That's what we find.
Okay. What?
Yeah.
Just a comment
Yeah.
that most of these galaxies at this redshift has a halo above this M star halo. So that roughly.
All right, very quickly, David. 30 seconds.
Can you say something about how bars fit into this picture and whether they are a totally separate kind of object or are they part of the picture of what you call prolateness?
We try to look for bars. In particular, we try to look at the rotation curves of galaxy to kind of see how many bars we have. But actually, we only estimated a fraction of bars of about 5% in the prolate system. So we do not have a lot of them. So at first we try, because there's a lot of work in the literature done for bars, and they claim that when you have a central mass concentration, you can actually destroy the box orbits. But actually we do not have bars. But still, we find that the larger the concentration is, the more oblate you become. So the two things must be related. We're discussing this, and we're still trying to figure out how to phrase it better. But yeah, that's okay.
Thank you.
Yeah.